All right, so the question of the day is, do you like green Skittles? In 2021, Skittles changed the flavor of green from sour apple to lime. That is true. I like the lime so much better than the sour apple. Lime was like their original flavor, and then they changed it at some point to sour apple. Not nearly as good. They changed it back in 2021 to lime. Yay. I take a small handful of 5 Skittles from a bin of 10,000 Skittles. So a bin with 10,000 Skittles in it, all mixed together. I reached in, grabbed 5 Skittles, and they all came back green, which made me happy because I love the green ones. Those are my favorites.
Green's the best flavor for stuff.
Agreed, especially Jolly Ranchers.
Yes.
If 20% of the Skittles are green, what is the probability of this happening? So I want you guys to stop for a moment and tell me whether or not this is a binomial setting. So use that acronym, use BINS. We did this yesterday. We did this on Monday. Go back and look at that if you need to. Check BINS and decide whether or not this is a binomial setting. I'm going to give you guys about 1.5 minutes, 2 minutes to decide if this is binomial.
Give me an example of something that wouldn't be binary.
That wouldn't be binary? So like yesterday with the quiz, we could talk about it as a binary setting. You either got the question right or got the question wrong. Or we could have approached it as, like, instead of what's the probability that you got 5 questions right, we could look at the different answer choices, in which case A, B, C, D, then it wouldn't just be binary. There'd be 4 options.
Okay.
Does that help a little bit?
Yeah.
So like instead of what's the probability that you got 2 right, what's the probability that you answered A on 2 of them? So something like that.
Is it just 45 or is it an independent?
Ooh, good question. So what would constitute a trial here?
Like one time grabbing a handful of 5 M&Ms, right?
Close.
Would it be each, or I said each Skittle?
There are certain circumstances where you could argue that grabbing a handful of 5 would be a trial, but we would typically more refer to that as a simulation. And the trial itself, because the thing that's either true or not true at the end is coming from each individual Skittle. All right, got about another 15, 30 seconds to decide whether or not this is a binomial setting.
Whether it's lime or apple. Like at work, we have these, they're not Dunkin' Donuts, but we have little lollipops. They used to be Dunkin' Donuts because then we got like an off flavor. But so they're for like little kids and adults, but like the little kids will always ask their parents. And so I'm always like, I like the green ones, but there's 2. There's either a lime or a green apple, and I'm like, I like both of them.
Fair. Very fair. All right, question. Is this a binomial setting? No. All right, so what does it violate? Is this a binary setting? Let's start there. Yes, so what would be a success?
Green.
Getting green, and failure would be not green, any other color. So we definitely have the B for bins. All right, I'm going to kind of move backwards here and start at the bottom now. The S, same probability of success each time? No. 20%? Yeah. What's N? 5. So we have a fixed number of trials. Is it independent? No. Yes. Yes, Audrey.
Okay, since it's not independent because it's not replacement, how would that not change the probability of grabbing each Skittle?
So you're actually correct, but we're going to look at that in a little bit more detail, but you are 100% correct on that. Technically speaking, we fail on same probability of success each time because we're not independent, because we're sampling without replacement.
That's why I meant.
Yes. So if you had an X for same probability of success each time, I would accept that. A lot of times when students read through this problem the first time, they grab onto that 20% and they're like, there's my probability of success. And they put that down for S, and so they check it off. And we'll see in just a minute why I would be okay with that, even though technically our probability of success is changing each time. Yes? How is there a fixed number of trials? What would N be in this case? 5. Each Skittle is a trial. It's not grabbing the handful that's the trial, it's each Skittle, because each Skittle would be analyzed, are you green or not? Are you green or not? Are you green or not? All right, so far so good? All right, I'm gonna give everybody a second to get this explanation written down for number 1. And then I want you to look at number 2. Find the probability of getting 5 green Skittles if this is not a binomial setting, which we already established that it's not binomial. So I want you to think, what is the probability that the first one is green, and the second one is green, and the third? What operation are we going to do? Multiplication. So what's the probability that the very first Skittle is green?
1 of 10,000. 20.
You said 20%. So how would I write that as a fraction? I could write it as 1 out of 5, but in this context, how many Skittles do we have? Because the fraction should have meaning, top and bottom. 1 out of 10,000 would be 20%.
No, it's like 2,000 out.
2,000 out of 10,000.
Yeah.
2,000 out of 10,000. Yes. So 20% of 10,000 would be 2,000. So as I'm thinking about the probability of getting all green, my first fraction is 2,000 out of 10,000. And you said we're doing what operation with each of these fractions if I want the and? We're going to multiply, yes. So this is the probability the first Skittle's green. What's the probability the second Skittle's green?
1,999 over 999.
There we go. Please go ahead, now that you've got that pattern down, calculate the probability that all 5 Skittles are green. Calculate the probability that all 5 Skittles are green. I'll give us about, since we got some calculations to do here, let's take about a minute, minute and a half. Because you're going to have to type it into your calculator.
It doesn't explicitly say that it's independent or that it's with replacement. Should we assume that it's without replacement?
Ask me that question again at the end of this lesson. I love the question. I think I'm going to answer it as we go through the lesson. Okay? What did you get for the probability? So this denominator right here. Ooh. Yeah, that's okay. You were really close. It's just those denominators. Watch those. All right. Let's first establish what the multiplication should look like. You guys have those fractions? All right. And then you got scientific notation, right?
Yeah.
You got the E thing. I want you to convert it into a number that's not in scientific notation. So write it just in its decimal form. What did you get on your calculator screen when you did this? What was your scientific notation that you had? Yeah, what did the calculator say?
187214079.
You said 3 point what?
187.
187 something something something, right? E to the negative 4. You remember this right here means we need to move our decimal point 4 places. Which way? To the left. So 1, 2, 3, 4. Decimal point moves right here. Fill it in with zeros. So I went ahead and rounded this to 0.000319. Or I could have done 3187. All right. Number 3. I want you to find the probability. We know it's not a binomial setting, but I want you to calculate the probability if this were a binomial setting. So I want to know the probability that all 5 are green. So what does my notation need to start with as far as how I'm going to write this out in formula form? How many trials did we have? 5. How many successes do we want? 5. So right after the equal sign here, what do I need? 5C5. What's it going to look like if it's part of a multiple choice? Because it won't say 5C5. Yeah, it'll be 5 on top of 5 like this. But the way you put it into your calculator is 5C5. So that's absolutely correct. And then what would we have after this? 0.2 to the power of 5, because we want 5 successes. And then times what? 0.8 to the power of 0, because we didn't want any failures this time. So 5 over 5, not a fraction though. 5 over 5 in this weird double-decker parentheses. 0.20 to the 5th, 0.8 to the 0, or 5C5, 0.20 to the 5th, 0.8 to the 0. Again, when you guys are writing answers for me on tests, on homework, I'm fine if you just write this down. But I want to continue practicing with this so that you know what to do with this to be able to put it into your calculator. All right, pop that in your calculator and tell me what you get. 3.2 e to the negative 4th. So that would be what in its just decimal form? 3.2 0.00032. What do you think of those two numbers?
They're very close.
Like, those are so ridiculously close together that as far as I'm concerned, that's the same number.
It's because 10,000 is such a big number that it's not enough of a difference to change the percent or the probability that.
Yeah, like when we were talking about this
5
not
Skittles.
being 5 Skittles out of 10,000, this is a drop in the bucket. Like, it barely makes a dent. Nobody's going to notice in a vat of 10,000 Skittles if you come along and swipe 5. Nobody's going to look at that vat of 10,000 Skittles and go, oh, somebody took some. They're not going to notice.
Exactly.
It's 5 Skittles. Can somebody put just this in their calculator, 1999 over 9999, and tell me what you get? What is 1999 over 9999? 0.1999999. So if you're going to write that down, that's basically 20%, right? 0.199999. All of these fractions, this one's exactly 0.20. This one's almost 0.20. This one's also about how much? It's about 0.20. So the answers here in number 2 and number 3 are almost the same. The probabilities in 2 and 3 are so similar because the sample is really small relative to the population. What's the population here? 10,000. And our sample size is 5. This brings us to the introduction of an important concept, because so often in real life situations, we have something more like this happen than having true independence. We call this our 10% condition, the 10% condition. We want little n, which is my sample, that's my sample size, to be less than or equal to 10% or 0.10 times capital N. If little n represents my sample size, what do you think capital N represents? The population. Capital N is my population. So what the 10% condition lets me do is look at a situation that's almost binomial, but it's violating that independence criteria. And now I can say, as long as my sample is smaller than 10% of the overall population, the changes that are happening when I sample without replacement are so small that we can basically ignore it. So we can treat it as if it's independent, even though technically it's not, because the difference in proportions is so tiny that we can ignore that difference. So far, so good? All right. Let's go down and look at number 5. All right, so now I grab a huge handful of 100 Skittles from the large bin of 10,000 Skittles. We're going to let our random variable x equal the number of green Skittles in the handful of 100. X can be considered a binomial random variable because the 10% condition is satisfied. How would I show that the 10% condition is satisfied? I would say 100, because 100 Skittles right here. We said it needs to be less than or equal to 10%, so 0.10 times my population. What's my population? 10,000. What is 0.10 times 10,000? 1,000. So as long as 100 is less than or equal to 1,000, which it very much so is, we have satisfied our 10% condition. Some of the scenarios that we look at, you're going to be able to actually do this because we will know the population size. In this case, I know I have exactly 10,000 Skittles. But if I was going to do a study about like the proportion of red cars, where my population is all cars in the United States, do we know how many cars there are in the US? That is not an easy number to get my hands on. But if I were to sample, say, 100 cars, would you agree that 100 cars is less than or equal to 10% of all the cars in the US? So in that case, when I don't have a number for my population, I will put in words what the population is here, and I will write out this inequality, and then I'll put a check mark next to it as long as that's a reasonable assumption to make. I would like you guys to calculate the probability of getting at most would mean what? What inequality do we use for at most? Less than or equal to. So at most, 11 green Skittles in this handful. We practiced calculating the less than or equal to probabilities yesterday. You can look back at yesterday's notes if you need a reminder. Go ahead and calculate the probability. We said this was basically binomial. So you're going to use your graphing calculator. Look back at yesterday's notes if you need to. We said this is a binomial random variable because we have our 10% condition met. I'm going to give us about another minute and a half to calculate this probability. Feel free to look back in your notes from yesterday for how we calculated the probability of a less than or equal to. What does my probability notation need to look like? What's it start with? P, parentheses, x is less than or equal to 11. Perfect. So that's where we're going to start. Probability that x is less than or equal to 11. What's the name of the function that we're going to use on the calculator? Binom CDF. Yes. Binom CDF. How do you get there? Second and vars, which gives us our distributions. If you look at the little blue letters up above, you're right.
And you go all the way down.
All the way down to option B. But it's found in the same place that we find normal CDF. You just have to scroll down further.
Or you could do second. Apps.
Yes. All right, so what are the 3 parameters that we need to feed into the calculator? We're going to put that inside parentheses here. Ooh. What is my N here?
It's how many trials, which is
100. Because we grabbed a fistful of 100. So I don't know why I wrote it like this time. Typically I will have this, and then I will have the N underneath it like this. All right, so we have our number of trials. That's the first number we feed into it. What's the second number we feed into it? Probability of green?
Like having a green skittle?
Yes. Probability of green, which we said was how much? 0.2. So again, I don't typically write it like this. Most of the time I would put 0.2 or 0.20. I don't care whether you put 0.2 or 0.20. And then we're going to have the P either underneath it or above it. If you write it inside the parentheses, it's fine. I just don't typically do it that way because it ends up taking up so much paper this way that I run out of room. And then what is the last number that we feed into this? The X, which in this case is 11. So I would have 11, close my parentheses. We're going to label that as X. This is the level of work that I need to see on a problem like this. You need to tell me the function that you're using right here. What are your parameters? Trials, probability, our x value, our boundary line. And then you hit enter and you get what? Yes. 0.0126. If you round it, if you just truncate it, 0.0125, I'm not going to get picky about that fourth decimal place. So over here, in this picture right here, this is the probability in a handful of 100 of getting, let's see, right here would be getting 10 green. Here would be getting 20 green, 30 green, 40 green. So these are all the probabilities in a histogram. We made one of these by hand the other day, but this was way too big to make by hand today. What is the approximate shape of this distribution? It looks like it is approximately what? Normal. That is an approximately normal distribution. We've got this bell shape to it. Ooh, there's my really bad bell shape over the top. Because x is a binomial random variable, we can use the formulas that we learned yesterday to calculate the mean and the standard deviation. I want you guys to find the mean and the standard deviation using the formulas that we learned yesterday. It's in that quick notes box if you need to go back and look at it. Calculate the mean and the standard deviation for our random variable x. Calculate the mean and the standard deviation for the random variable x. Nice.
It's weird that it's like a
Perfect number,
final number.
right?
Yeah. But it's because
Mm-hmm. Yeah, it doesn't normally happen, but on this one, it came out nice and pretty. Doesn't happen very often in the wild, but in fabricated examples, it can show up a little more often. What is the mean? 20. N times P. N is 100. That's my number of trials. Probability of success is 0.2. So my expected value, my mean, is 20. Absolutely, very good observation. When you're looking at this probability distribution, where is 20? Right in the middle. It is the mean, it is the center of this distribution. That's the highest bar on our histogram. What is the standard deviation? 4. Square root of n times p times 1 minus p, so we have the square root of 100 times 0.2 times 0.8, and we get exactly 4. So we said that this was approximately normal with a mean of 20 and a standard deviation of 4. So next to this distribution, I'm going to put a big capital N for normal. And then my labeled mean of 20 and my labeled standard deviation of 4. I want you guys to redo the calculation from number 5 up here, but I want you to do it with a normal distribution. Instead of a binom CDF, I want you to use normal CDF.
Would our upper boundary be 100? Because you can only pull 100 green Skittles.
So think about the direction of the shading. Are we doing a greater than or a less than? What did number 5 say?
Oh.
Yeah, we have a less than or equal to. Take a moment to redo number 5 using a normal distribution. Oh, I apologize.
I don't know if I'm just like blanking, but how are we getting point? Oh, we're still looking at this one. Oh, okay.
20% are green.
Oh,
Yep, that's where that 0.20 is coming from.
I thought this was like completely different.
Oh,
Probably not, it's like-
no, my apologies. We still have this big vat of 10,000 Skittles, but instead of just grabbing 5, now I'm going to grab like a fistful of 100.
Oh, okay.
Yep. But other than that, it's the exact same parameters, exact same setup in that upper box. Good to go. Make sure you catch the video for what you're missing. All right. So let's talk about this one. First of all, if I'm doing a normal CDF, I still have to start this with probability notation. What does my probability notation look like at the beginning? What'd you say?
P is x less than or equal to 11.
Yep. P parentheses x less than or equal to 11. Always want to make sure that we're getting that probability notation down. And then we're using which function again? Normal CDF. And then we have to put our parameters inside parentheses. What are the 4 parameters we need? Mu, which is the mean. Sigma, the standard deviation, yes. What could we use as a lower boundary? Stick a negative on the beginning, yes. Negative 99999. Or we could use 0. In this scenario, 0 would make sense as the lower boundary because you can't have negative green Skittles. So when I did this, I did go with something stupid small. I used negative 1,000,000. If you use negative 9999, that's fine. If you use 0, should be fine. Next number? 11. Make sure you're labeling these as the lower boundary and the upper boundary. And then what 2 numbers do I still need? 20 and 4. Mean and standard deviation. And what did you get when you did normal CDF? Yeah, I got 0.0122-ish. What do you notice about the answer from number 5 and the answer here on number 8? So if I were to talk about this one in terms of percent, that's 1.26%. This is 1.22%. Is that a very big difference? No. For all practical purposes, these are basically the same. These are almost the same. Almost the same. So my binomial distribution has a lot of similarities to my normal distribution, but only if a certain criteria is met. And we call this criteria the large counts condition. The large counts condition. There's a reason I didn't have us try to do a normal CDF when I was only taking out 5 Skittles. There's a reason that I set it up again by saying, okay, now I'm going to grab 100 Skittles out of this big vat. The large counts condition says that if n times p is greater than or equal to 10, If n times p is greater than or equal to 10, so this would be the expected number of successes and n times 1 minus p is also equal to less than or greater than or equal to. Let me read the correct inequality. Greater than or equal to 10. So again, this then would be the expected number of still successes?
That's failures.
That'd be failures, yes. So as long as I expect to have at least 10 successes and at least 10 failures, then my distribution will be approximately normal. Approximately normal. If my large counts condition is met, then my distribution will be approximately normal. All right. So, oh, that's the wrong thing. Clicked on the wrong thing. Try it again. Go ahead and flip this over. We're going to look at our quick notes now. Here we go. This is what I wanted. All right. 10% condition. When taking a random sample without replacement of size lowercase n, this is what we use to represent the sample, from a population of size capital N, we can use a binomial distribution as long as the sample is less than or equal to 10% of the population. The sample size is less than or equal to 10% of the population. And this is specifically when we're looking at without replacement situations. If it's with replacement, then we are independent and we don't have to worry about the 10% condition. Large counts condition, we're going to use a normal distribution to model a binomial distribution as long as I expect at least 10 successes, at least 10 expected successes, and at least 10 expected failures. Looking at these two criteria, does it make sense why we're calling this the large counts condition? Yeah, I need my counts for successes and my counts for failures to be big enough, which the threshold that was decided for that is 10. And if we have time, I'll pull up some graphing software and show you why 10 was decided on for that threshold. All right. I would like for you guys to spend the next 5 to 6 minutes doing the check your understanding down at the bottom. Spend the next 5 to 6 minutes doing the check your understanding down at the bottom. So read through the problem. In number 1, I want you to explain why the random variable x is allowed to be modeled by a binomial distribution. Then I want you to use the binomial distribution to make a prediction for an estimate, or rather to find the probability. Then decide whether or not it's appropriate to use a normal approximation. And then I want you to use a normal distribution. So take about 5 or 6 minutes. If you need help, I am more than happy to help. We're doing the check your understanding now. You good, Mariah? You all right? Okay, let me know if you have questions.
Just realistically, that 65% eat breakfast. The students eat breakfast before going to school.
It's a strong assumption. Let's just
I ate
assume.
mine after going to school,
Fair.
but that was rare. I usually don't eat breakfast
At all?
because I just had to wake up early. So it's like, let me eat on my food.
Fair. Do you have any questions? No? Okay. You doing all right? You doing all right? No, that's fair. I understand. I just want to make sure that it's not because you're frustrated. Okay. Doing all right, Luke? So what do we need to check to make sure it's binomial? So go through and check things. We know we're doing this without replacement, but there was something that we talked about up here that we can use even when we're not sampling without replacement. That's a good question. Okay, so in this case, it tells us says of high school students. So our population then would be all high school students. Got about 1 more minute and then we're going to go over this. All right. Explaining why a random variable can be modeled by a binomial distribution means that I need to check bins. So the B stands for binary. Is this a binary situation? Yes. So what would constitute a success here? Eat breakfast. And so then failure would be not eating breakfast. Now, one of the things that I want to stop and talk about for just a second is when we talk about binomial random variables, we talk about it in terms of successes and failures. But by success, I just mean the event that I'm interested in. Sometimes the event that I'm interested in is like how many people got fired, or what's the probability of getting fired. So in that case, success would be getting fired, which is not a good thing. But we simply are terming success in regards to what's the event that we're interested in. What are we going to be counting here? All right. Is it independent? Is it independent?
Yes. If we're making it binary.
I don't think so.
It is not independent. We're not sampling with replacement. People can't get picked more than once. So once I take somebody out of the population, they don't have the opportunity to be selected again. So it's not independent. But there was something that we talked about in this lesson that can deal with when I'm sampling without replacement so that I can still get a check mark for my independence criteria. 10% condition. So my sample size has to be less than or equal to 10% of the whole population. What's the sample size here? 500. What's the population? We don't know. Are we looking at just one school according to this? No, we're looking at high school students. So the population would be all high school students. We always want to get that word all in there so that we're making it really, really clear that we're looking at everyone. 500 is less than or equal to 10% of all high school students. So we get our 10% condition met here. This is what I would want to see as far as work goes. Weird, sorry. This is what I would want to see as far as work goes to justify when it's not independent, but we're going to go ahead and say it's basically independent. I would want to see this written down here. Number of trials is fixed. Is that true? What is our number of trials? 500. Thank you. Number of trials, n is 500. Same probability of success each time. Yes. How much? 65%, yes. Technically speaking, does it stay exactly 65% each time? No, because we're sampling without replacement. But it's so close. When we're talking about all the high school students, my probability of success is going to stay approximately the same, like we saw happen in that Skittles example where I had 10,000 Skittles. So this right here is why we can go ahead. That was a bad color. Try a different choice. This right here is why we can go ahead and use a binomial distribution. It met all the other criteria, and then we met our 10% condition, which gave us independence, or approximate independence. Use a binomial calculation to estimate the probability that 300 or fewer high school students in the sample eat breakfast before going to school. What's my probability notation look like? P and then X less than or equal to 300. And what function are we going to use on the calculator to do this? Binom CDF. What are the 3 parameters that we need to feed into it? 500. Make sure you label that as N when you write it down on your page. 0.65. Make sure you label that as P when you write it down on your page. And then 300. Make sure you label that as X when you write it down on your page. And what did you get? 0.0113, which is about 1%, right? 1.13% is about 1%. Right, number 3. Is it appropriate to use a normal approximation? Is it appropriate to use a normal approximation? What do we need to check to see whether or not this is appropriate? This is one of the other new things that we learned in this lesson. NP needs to be greater than or equal to 10. What is N times P here? 325, which is greater than or equal to 10, right? What else do we need to check? Not just N times P.
N times 1 minus lowercase n.
Yep, N times, not lowercase n, N times 1 minus P. And what does that come out to be? 175, which is greater than or equal to 10, right? Question. These 2 numbers add up to what? Don't grab a calculator. 500. If I expect 325 successes, then I would do 500 minus this. That's my expected number of failures. So is a normal approximation appropriate? Yes. Large counts condition is satisfied, so a normal approximation is appropriate. Number 4, you need to have a picture. This would be the beginnings of my picture. 325, my mean, right down the center. We want less than or equal to 300, so I have 300 on here and I have it shaded to the left. What do I need next to the picture? N with the mean, which we already know is 325. What's the standard deviation here? 10.67, 10.665. I don't care where you round it necessarily. If you do 10.67, your answer will be close to mine, but not exactly, and that's okay. So we have our mean of 325. We have our standard deviation of 10.665. Then we do normal CDF, lower bound, upper bound, mean, and standard deviation, and we get what? 0.00966954. It's about 1%. Just like when we did our binomial distribution, it's about 1%. All right. Tomorrow, we will be doing the last lesson of chapter 6. When is homework due? Tuesday. Tomorrow is the last lesson. Homework is not due until Tuesday, though. Have a great rest of your day, guys, and I will see you on Friday. Please make sure to put up your graphing calculators.